Let's review the rules for means and variances together. We're going to use this example in a casino where there's a gambling game where it's possible to lose $1, break even, win $3, or win up to $5. And here are the probabilities of doing that. This is the probability distribution. In other words, this is presenting to you the population information on the variable, how much a person's going to win, right? So the variable is winnings, and the winnings are -1 up to $5. With the different probabilities, the probabilities sum to 100%. Because these are, this is the information on the population, any average we calculate, the mean, could be referred to as mu x. Remember, this is the symbol we use for the mean of the population, not x bar, which is the mean of the sample. To calculate this, well, notice this is a discrete distribution because we only have 4 possibilities, and I can put them in a list with probabilities. Okay, so this is a discrete distribution. In this discrete distribution, to calculate the mean, we simply multiply to get the weighted mean. We multiply and sum weight times mean, weight times score times weight times score times weight times score, weight times score, and you add those all together. Okay, this is the formula for the weighted mean. Now you remember we've used this before, but the data that I gave you before was the sample data, not population data like this. Okay, so that is the mean. In this example, computing the mean, the weighted mean, multiplying -1 times 0.3 would be -0.3, 0 times 0.4 would be 0, 3 times 0.2 would be 0.6, 5 times 0.1 would be 0.5, and now I sum those to get 0.8. So that's the mean of this distribution, 80 cents. What we're going to do now with the mean is discuss 2 rules for the mean, and the idea of these 2 rules, they're intended to simplify your calculation of the mean and variance for a different variable, that depends, however, on the variable that you already have. So let's say I have information on x, and I create a variable y that is made up of x somehow, and I'll show you the ways that we can speak of. And if that variable is made up of x, then we can use the fact, the mean and the variance of x, to draw conclusions about the mean and the variance of that new variable in a simple way. Let's look at rule number 1. This is the linear transformation rule, and it's motivated by considering a new variable. Say I created a new random variable that was made up of x, the original variable, and I take each value of x and multiply by some value b, and then I shift the whole distribution by adding a constant value a. Alright, for instance, there's a problem on the bottom. Here, for instance, we're going to take the original gambling game, but since the casino realizes it's losing money, they decide to adjust the payout levels by subtracting $1 from each prize. So this is the new distribution. Alright, and the new mean of that distribution, well, we'll just calculate it in the original way, multiplying these together, plus multiplying these together, plus multiplying these together, plus multiplying these together. So that's the new mean. So now on average, a person is losing 20 cents rather than on average winning 80 cents. A simpler, faster way to do that using the rule on top is to take the rule. The rule says that if I want the mean of a linear transformation, so in this case the random variable x, every value, the possible values was subtracted by 1, then the new rule, or the new mean for the new variable, would be a matter of just subtracting the mean by 1 as well. Okay, so you can take the original distribution, the mean of that, and subtract that as from 1, and you would get, using its mean, 80 cents minus $1 leaves a new mean of 20 cents, negative 20 cents. And that's pretty much the rule on top. Okay, so all you have to do is do the same thing you did to each value, do it to the mean. That's what it's saying. And this is only in the case where you either add or subtract a value, or multiply or divide a value to the mean, or both. You might be wondering why we have such a rule when it's easy enough to just recalculate, like in the bottom here. We did a fine job just recalculating the mean, you see, to get this value. Why did we need to use the rule, you might be asking yourself? Well, we're just introducing you to the rule here in this course, but in fact, the rule could be used for much more complex distributions, even continuous distributions. The distributions don't have to be discrete like this. This is just to show you how it works and how you could get such an answer using this rule. Okay. On page 38, here's another application of the rule for a linear transformation. In this case, what we're going to do is not only subtract 1, but we're going to take that result and multiply by 2. All right? So this makes the mean even lower. So it's going to be negative 40 cents. A faster way, well, to apply the rule, I'm going to say it's a faster way, but to apply the rule, what would we have had to do? Well, this is essentially what we did. We took each value minus 1 and then multiplied the resulting value by 2. I need to put this in the form of the linear transformation, so I do multiply it through. And so this is what I'm going to do. The A is minus 2 and the B is 2. Okay, so just to show you the steps, taking the mean of this new variable, leaves the negative 2 intact, and then the mean of 2x becomes 2 times the original mean, and that's how we get the same value, negative 4, by now plugging in 2 times the original mean of 80 cents, subtract 2. Now the second rule for means. Second rule for means essentially is that the mean of a sum of variables is equal to the sum of means. All right? The mean of a difference of two variables is equal to the difference of the means. If I wanted to consider coincident winnings at this casino of two different games, then all I would have to do is find the mean of the two different games, and then if I'm looking at the coincident winnings, or the sum of my winnings, then I would just sum the means. That's the mean of the first one. This is the mean of the second one, so I simply sum the means. So in this case, the losses of playing two losing games, on average I would lose 30 cents. Now let's take the original gambling game and compute the variance of the distribution. Here's the distribution, remember? All the probabilities sum to 1. How do we calculate a variance? Remember, this is the distribution as determined by the population. So because of that, the variance notation will be a sigma squared. And we just use a little x subscript just to say we're referring to the random variable x. And it is the average square deviation from the mean, remember. So average square deviation from the mean is actually equivalent to just the mean, the expected value of the squared deviation from the mean. And that's what we're doing. This is the mean, and this is the squared deviation, where we use a capital X because we know all the values. We often use capital X when we know we're referring to all the possible values of the population. Okay, not the sample values. And here is the weighted squared deviation from the mean for each case or each state, and we sum them up. So this is the average squared deviation from the mean, but the weighted average squared deviation from the mean. And below here is a calculation where I've taken, using the mean that we know of 0.8 and subtracting, calculating the deviation, squaring it, and then weighing it by its appropriate probability. And doing that in each case, summing it, and there's the variance. From this, we could take the square root and calculate the standard deviation. A second formula for the variance is given by this notation. This just shows that we can get the average of the squared values of x and then minus the squared mean. It's just another way that's often used in statistics to calculate the variance. I prefer this method. All right, let's look at the properties of variances now. Let's refer to the example we saw before where we took the gambling game and we did two things to the original gambling game. First, we subtracted each of the outcomes by -1 and then multiplied the results. And these are the same probabilities but the new possible outcomes. And with this, we could calculate the variance using the formula, understanding it's the average square deviation from the mean, and the weighted average particularly in this case, and that would give us the variance. So here's the calculation all worked out, and this is the new variance, 15.84. Is there an easier way to do this? Rather than having to recalculate the variance? Well, in fact, there is, just like there was for the means. The rule is, it's right here. If we were to take each value of x and multiply it by a single value and then shift over the whole distribution by another factor a, the shift factor would not affect the variance since, remember, variance is the average square deviation from the mean, and if every value was shifted by the same amount, this wouldn't change the deviation from the mean. So all that's going to matter is the amplified value, the b, and so that gets squared just because of the formula, remembering that we square the deviations from the mean, so the b would get squared in the process. All right, so if we were to, rather than recalculate the variance, use this rule, then this is the transformation, which we write in the a plus bx form above by just distributing the 2 through the brackets. And notice the -2 drops out, and all we have to do is take the variance of 2x, which the 2 becomes 4, because that's 2 squared makes 4, and that's for variance of x, and the original variance was 3.96, so the new variance is 15.84, just like we got by calculating the variance of the new distribution. Now the variance of the sum, or the difference of random variables, it's going to depend on whether there's a relationship between the two variables to determine the new variance. All right? If the variables are independent, then the sum or the difference will have a variance that is the sum of the two variances, the original variances, okay? This is because variance is, again, the squared deviation from the mean, and subtracting the two distributions from each other doesn't subtract variances, it compounds the variances, just as it does when you add the random variables. If the variables are not independent, so there's a correlation between the variables, then there's a third term. If you're adding the variables together, then we're adding 2 times the covariance. If you're subtracting the variables together, you're subtracting 2 times the covariance. A second way to write this is based on the fact that the covariance can be standardized as the correlation. The correlation of x and y is just the covariance of x and y, standardized by dividing by the standard deviation of both of these. Rewriting this by taking, by solving or isolating for the covariance, gives that and this is your substitution, where sigma x, sigma y times correlation, so this 2 standard deviations times correlation is equal to the covariance, and this is the substitution here. In general, we should be able to extend this pattern for more than 2 variables. If we were to sum or subtract a number of variables, this is if we wanted the variance of the sum, let's say, of many variables, then this would be equivalent to this. Now, what the heck is this? Well, you should think of this as generating a matrix of covariances. So a matrix like this, think of taking x1 and x1, the covariance of that. What would that be? That would be the variance of x1, as would all the terms down the diagonal would be variances. And then the other terms, see these two? These are identical. If you're taking the covariance of those and summing them, then really what you're getting is the covariance of x1, x2, but 2 times, because there's 2 of them. And similarly, for for x1 and x3, did I do something? This is a 1 here. Okay, so that's for x2 covariance of x1 and x3, and then the last one would be 2 covariance of x2 and x3. Okay, so the only question you might have is how is this the variance? If I take the covariance of x1 with x1, oops, that's x1 with x1, that's going to be the same as the variance of x1. All right, so all these terms are sum. That's what this formula says, sum all the matrix terms of the covariances in all combinations of x1, x2, and x3. And that's what we get. So that's the general pattern. The only other thing we have to consider is well, we might want to do a subtraction. We might want to do 2x1, something like 2x1 plus minus 3x2. What if we wanted the variance of that? How would we figure that out? Well, we need to know how to treat the constants in front, right? These terms in front, coefficients in front. And so this is why I have this final rule. If you want the covariance of two variables and they have been adjusted by a coefficient, then it's just identical to having the coefficients outside and the original covariance. So with these several rules, you should be able to complete the following exercises. And I encourage you highly to try the exercises without looking at the answers, and then refer to the answers to see if you got it right.